Hello and welcome to Noel's Retro Lab. Today we're going to be looking at this Apple IIe. It's the first time we're looking at any Apple II in this channel. To be honest, today's episode was supposed to be a little different. I pulled out the Apple to shoot something else and then I noticed that it had no video out. So I started looking into it and digging deeper and deeper, and eventually I unraveled a bunch of interesting things. So today is going to be a deep dive into the color generation of the PAL Apple IIe. Let's get started. So here it is, the Apple IIe. This wasn't nearly as popular in Europe as it was in the US, and the US managed to make it into education, so almost every school in the 80s had some version of the Apple II computers. So this one in particular is the PAL version. I think in the back, those are the different connectors, but somewhere, yeah, right there. Right there, it says this is the PAL version with a specific type of model number. And one really cool thing about these Apple II computers is you can tell by the way the case was designed that they want you to get inside and do things, because you don't have to remove any screws. You just lift those two tabs back here. Oh, sounds easier. There we go. Like that. And the case pops open, just like that. And it exposes everything inside. You could put in cards, you could do whatever. So this is a nice change from all those computers that have you remove tons and tons of screws to get inside. Or even have signs in the back like the Amstrad is like, do not open this, you void everything. It's like, nice refreshing change. This was also earlier in time. This was, the Apple IIs were made in the late 70s. This model specifically is from 1982, and that's even earlier than some of the other computers that we're seeing, like the Amstrad or ZX Spectrum. All right, enough introductions. Let's fire it up and see what we get. That's not what I was expecting. There's no color there. I knew the color on the Apple II was very dodgy, and that's because it's really such an early machine. The Apple II is actually mostly a monochrome machine, but it just so happens that if you place the dots in a certain patterns on the NTSC display, they'll produce an interference and create color, so almost like the color is a side effect. That's actually why the Apple II doesn't have a large set of colors that you can set in your palette. It just has a fixed set of colors. They're limited to whatever the interference creates. Since this is a PAL machine, you can't rely on the specifics of NTSC interference, so I was afraid that we would just get a monochrome image like what we're seeing. But then I remembered that on PAL boards, they have a switch to toggle between monochrome and color modes, so hopefully that's it. No, that's still not doing it. It actually looks a little different. It looks like in mono mode, the image is higher frequency, so the patterns probably don't produce any kind of interference and they're displayed as monochrome. That's great for text, but pretty bad for games. And when I turn on the color mode, they seem to kind of merge more together, but we're still seeing it in black and white here. So what's going on? Is there really no color on PAL systems? So I did some searching, and while I found out that you can get color out of PAL systems, I also found out that lots of people had trouble with them. So it looks like I'm not the only one with problems. Just to rule out my TV somehow not liking the signal, I'm going to try feeding the composite signal into my video capture device, and maybe I'll manage to get a correct color image. Yeah, no, that's not happening. It's actually worse. It almost looks like he manages to get a correct image one frame and then he loses it and then he catches it again. Okay, one more test. I'm going to change TVs and try to display it on my LCD. It usually has much worse image quality for retro computers, but maybe it accepts a wider range of PAL signals. I don't know. So let's see what it looks like there. All right, that's interesting. We have color, but the color looks weird. That's not what I was hoping to get. And what about the mono mode on the LCD? Yeah, that's more or less what I expected. The lines are more spaced. There's a little bit of interference, and so it generates some color, but that might just be an artifact of the TV itself. I asked some friends over at RetroWiki that had PAL Apple IIs if they could send me a picture of their screen with the colors they're getting, and this is what we got. So clearly we can get much better colors than what we're getting here. Okay, I think at this point it's pretty clear that the problem is not in my TV, it's on the Apple IIe. It's just not outputting a correct PAL signal. So in order to fix this, let's go back and look at exactly what a PAL composite signal looks like. We already saw some of this a few videos ago when I did a composite video mod for the ZX Spectrum. I'm putting a link to the video in the corner, but let's have a look at it again. An analog composite video signal is actually pretty simple. We're going to be sending all the lines in the screen, so the first thing we need is a marker for whenever each line starts. This is usually called a horizontal sync. Then we follow that marker with a signal indicating how bright each pixel is for the rest of the line. And we repeat this for all the lines in the screen, and there you go. That's pretty simple, right? What we've done so far works, but it doesn't have any color information. Our signal just says how bright each pixel in each line is. So how do we extend it to color? We could send the signal 3 times, one for R, G, and B, but that's just way too much information for the time when this video standard was designed. Instead, we can cleverly use a subcarrier wave to indicate the color at each point. That's called the Chroma Signal. The Chroma Signal is of much higher frequency, usually around 4 MHz, and starts with a color burst, which is used as a reference for the rest of the line. Then, depending on how the signal is shifted at each point, it indicates the color at each pixel. When you combine both the luminance signal and the chroma signal on top of each other, you end up with a composite video signal. Notice that it has all the components we talked about: the horizontal sync, the color burst, the brightness information, and the high frequency wave on top indicating the color at each point. Very clever. So first of all, let's check the composite video signal right at the video out and just see if it has a color burst in the signal. And I'm not seeing anything. That sure doesn't look like it has one. So here, most of the frames are black because we're only seeing a black screen with the Apple II. I wonder if this is like a black and white mode. I should try running the game and see if we see the color burst in there. Okay, yeah, it showed up right there. I'm gonna zoom in a little bit and I'm gonna try to stop it. There we go. So that's the color carrier, the color burst right there, which has the color information. And I can't see in the oscilloscope if it's correct or not, but at least I see that it's there. So that's start. And it makes sense because on the LCD monitor, we actually see some color. It's just ugly color, but there is some color. So that makes sense. Where does the Apple IIe generate this video signal? Over here. Yes, just about all of this is involved in the video signal generation. But we can identify some important bits. Over there is the quartz crystal used to generate the frequency of the color subcarrier. In the case of the PAL system, is 4.4 MHz. Also right next to it, it looks like there's an adjustable capacitor. Usually that helps adjust the carrier ever so slightly to make sure that colors are displayed correctly. So the next step is to check the signal out of the crystal oscillator. This is a, 4.4 MHz. And this is used for this is the master signal for the video signal itself. So it looks really good in the oscilloscope. This is 4.433 something, and that's exactly what it's supposed to be, 4.433 something. I suppose it could be a little off in the frequency. I'm not sure. I doubt that is that accurate, and maybe it matters. I don't know. There's an adjustable capacitor right next to it, and this I suspect will affect I don't think it affects the frequency, but it will affect the amplitude. So that might help a little bit. I know with some other systems like the VIC-20, this happens a lot, and you just tweak that a little bit and boom, instantly you go from black and white to color. So let's try changing it. And okay, the waveform changes, gets smaller, Oh, interesting. So it doesn't have a limit. I just keep going around and it alternates between making it larger and making it smaller. But it makes absolutely no difference on the video out. And I'm not sure what it's supposed to be, whether it's supposed to be larger or smaller. Because I'll leave it right there. But yeah, it made no difference whatsoever. Maybe the frequency is off. That kind of thing happens sometimes. Some of those crystal oscillators will, with time, decay a little bit and their frequency is slightly off. I mean, like right now it's saying 4.4, but then it's saying 4.2. That's probably just the accuracy of the oscilloscope. Still, it's an easy replacement to try to put another one, and I don't know if maybe the ZX Spectrum has that kind of quartz. I should check, and if so, maybe I can do a quick test. And indeed, the ZX Spectrum has a quartz crystal of exactly that frequency. So this is a spare board that is already missing a bunch of pieces. So this is perfect. I'm going to take it out and put it on the Apple II and see if that helps. And now we need to do the same thing with this one. With the new crystal in place, let's try the color diagnostics. And nope, still no color. One final thing we can try to see if the composite signal out of the Apple IIe is reasonable at all is to hook up this RF modulator. This came, I think, from a ZX Spectrum, which has them built into their board. And if you remember from the time we did the Composite Video Mod, we're actually going to do the opposite. To do the Composite Video Mod, we pretty much took the signal that was coming into the modulator, bypassed everything, and just hooked it up in there directly. The Apple IIe only has a composite signal, so what we're going to do is put the composite signal in the input, hook up ground and 5 volts, and hopefully we'll get some kind of reasonable RF signal there, and then it'll be curious to see if it has color or not. So let's give that a try. So I hooked up the RF modulator to a breadboard and then the signals to the Apple IIe board like this. We get ground directly from here. We can get it from anywhere, but we happen to get it from the composite connector. We get the composite signal directly from the connector itself, from the middle. And then we grab 5 volts from a resistor here that happens to have 5 volts. And again, we could just grab it anywhere else. And those are the 3 only connections that we need for the RF modulator to work. So let's turn this on and see what happens. There's definitely an image there in the signal, but we can't tune to it. There's hints of text or something, but nothing that we can really see. Since that didn't work very well, I'm going to try adding a decoupling capacitor. So a 1 microfarad, and maybe that will also help even the levels of the composite video signal, which I thought was higher than the composite video signal of the Spectrum, which is what this modulator came from. So I'm just going to disconnect the composite signal, hook it up somewhere like there, and then just put the capacitor like that. Just like that. And let's give that a test. Wow, we get some text. Yeah, that's way more encouraging. I mean, it looks horrible, but let's see if we can adjust the tuning a little bit so if we get a better signal. Nah, that's about as good as it's gonna get. And all of this is in black and white, so let's try the color. That's the whole point of doing this test. Oh wow, so we even lose the syncing to that signal. I mean, we kind of see it, but yeah, we're way worse off. So yeah, this RF modulator is also not able to deal with the composite video signal, which, yeah, it just confirms there's something really wrong with it. It turns out all of the circuit was added on top of the NTSC Apple IIe board to generate the color PAL signal. On the NTSC circuit, the dots in the screen are generated serially, and those show up over here. But we can't just bring those over to the PAL signal just like that. We need to actually convert them to a color. So the first IC over here is an LS164. That one will take in the dots serially and create a 4-bit number for every pixel. Now the timing needs to be very, very precise to get the right amount of dots in, generating the right color, but that's the way it's set up. The 5th bit actually represents the luminance of the image, so the brightness. So that means that the Apple II can only have one brightness level, either dark or bright, and then the only other parameter is the color itself. The luminance of the image seemed fine, so I'm going to assume that path is correct, and we're going to focus on the color, which is the other 4 bits. Those bits are added through a series of summing resistors into 2 signals, R minus luminance and B minus luminance. So let's look at them on the oscilloscope. I'm using the color diagnostics program to display a solid block of light blue color. And what we're seeing here on the oscilloscope is the red minus luminance signal. And as we would expect, in between each horizontal sync, we see this uniform block of blue color. Now this is positive because the signal is actually inverted. So the more positive the voltage, the more negative red minus luminance is. Now let's look at blue minus luminance, which should be somewhat the opposite of red minus luminance. In this case, the signal goes negative because blue minus luminance should be somewhat positive. So, okay, that matches what we expect to see. Now let's change the program to display a block of orange. And what we're seeing is that the red minus luminance signal shows as negative, meaning there's a positive value. And then when we look at blue minus luminance, it becomes a positive signal. So it looks like it's taking into account correctly both red and blue colors. Now let's turn our attention to how exactly the color is encoded in that 4.4 megahertz carrier wave. So this is done with the TCA650, which is actually a demodulator, but is set up in a clever or hacky way, depending on how you want to think about it, to actually serve as a modulator. It's going to modulate the color into the carrier signal. In order to do that, it needs to manipulate a little bit the basic carrier signal, the 4.4 megahertz signal coming out of that clock. And it needs to do 2 different things. One for the blue minus Y signal and a different thing for the red minus Y signal. For the blue minus Y signal, what it needs to do is actually offset the clock by 90 degrees. And this is accomplished in the small circuit out of pin 13. It's just a few resistors and capacitors, and that's enough to offset the signal by 90 degrees, and the result is fed into pin 9. And that's exactly what we're seeing in the oscilloscope, so that part looks good. And then for red minus luminance, what we need to do is invert the carrier wave every other line. That's actually one of the basic things of the PAL system. PAL actually stands for phase alternating line. That's exactly this. So for that, we have a signal coming into pin 16 that determines when the carrier wave needs to be inverted. The TCA650 will take care of it, and so the regular carrier will come out on pin 15 and it will be fed inverted into pin 11. So if we examine those 2 pins, we should sometimes find them completely inverted and then sometimes the same. And here we find the first potential problem, which is I was never able to see them inverted. Those 2 pins always had the same signal all the time. So there's something going on in here. Maybe the TCA650 is not working properly and is not inverting that signal. Looking at pin 16, it looks about right. We get a pulse every time there's a new horizontal line, so matching the horizontal sync, which is the indication to the TCA650 that it needs to invert the red minus Y carrier signal. So I just realized I misunderstood the logic on pin 16. That's not supposed to be a pulse to let the TCA650 to know when to invert the carrier wave. It's supposed to invert it while it's high and not invert it while it's low. So there is something wrong in the logic that generates the signal on pin 16. And that is coming from a flip-flop, an LS74. So the flip-flop has its negative output tied to its input. So every time it gets a clock signal, a step signal on pin 3, it's going to invert its state. The clock signal itself comes from horizontal sync, so it's going to happen at the beginning of every line. So at the beginning of every line, the output of that flip-flop should flip and stay flipped until the beginning of the next horizontal line. And it's not doing that. If we look at it in the oscilloscope, we see the input in yellow and the output matches it exactly. So it's not holding the input at all. And then as a matter of fact, if we look at the negated output, so that would be pin number 6, it's not even the true negation. It's holding this weird 1 volt and then going to 0. So I'm going to guess there's a short inside this flip-flop and it's not behaving properly, which is causing the TCA 650 not to invert the red minus Y carrier wave every other line. So it looks like the flip-flop LS74, it's faulty and we should replace it. So that's the one we need to replace. On this particular board, this chip was very challenging to desolder. I used my desoldering gun as usual, and it just did not budge. That happens sometimes with older chips, and depending on the boards. So when that happens, I just resolder it and desolder it, and that usually helps a lot. But this was a particularly stubborn one. It did not come out even with the second soldering and desoldering. I'm showing you this so you see that it's not always perfect. Sometimes you desolder something and it comes right out, and sometimes you have to do it 3 or 4 times for particularly stubborn boards. Alright, after the 3rd time, it finally worked. So now we can move on and replace the chip. Okay, so first of all, let's check that we're getting the right signals. And that looks right now. So the yellow one is the pulse saying that we need to switch polarity. And then the blue one is the signal holding during all that time is the output of the flip-flop telling the video chip to then reverse the polarity of the red carrier. So that looks very promising. Okay, let's give this a test. There you go, beautiful. You can see those colors, all the reds showing up. I think this looks great. Now let's try a game. Yeah, Choplifter looks exactly the way it should. Awesome. So this is interesting because looking back, we can actually see why certain things were happening. When I tried that video capture, it almost looked like it was capturing every other frame. Well, that's because every other frame, the red signal was correct. But then in the next frame, it was supposed to be inverted and it wasn't. So then it was losing sync and it was trying to catch again. So that makes a lot of sense. And I guess the Sony Trinitron TV just didn't see a correct PAL signal and just threw it all out the window, whereas the LCD one tried to do the best it could with it and it just said, oh, I can't make any sense out of the red channel, but it displayed the blue one. It's kind of cool when everything falls in place after you figure out what's happening. And there you go. In spite of the hacky video generating circuitry, the Apple IIe is outputting vibrant colors again. Now I can go back and film the episode I was hoping to do in the first place. And speaking of episodes, I have an announcement to make. I've started this channel about 6 months ago, and since then I've been making 1 video every week and then sometimes 2 videos when I do the shorter nibble edition. As some of you may know, I'm a game developer, and just recently I started a new project that is going to be taking more of my time. So until the project is over, I'm going to have to relax my release schedule, and I'm probably going to shoot to make 1 video every 2 or 3 weeks instead. Hopefully once the project is over, and it will do very well, I'll be able to pick this up again to a normal 1 video per week pace. So anyway, I hope you enjoyed this video. If so, as usual, give it a thumbs up and subscribe to the channel. Until next video, see you then.